Okay, welcome back everyone. Let's go ahead and get started again. So welcome to day 2 of this Introduction to Reinforcement Learning. So yesterday we covered some basics, the formalism of the full reinforcement learning problem, the decision theoretic planning methods for the Markov decision process, and the core reinforcement learning methods for learning without a model. Everything that we talked about yesterday made the assumption that the value functions and the policies that we compute or learn, that they'll be represented in a big table with one entry in that table for every state or state action pair. So today we're going to remove that assumption by replacing that table with some kind of a function approximator. And this will lead us down the path that will end in deep reinforcement learning, which we will cover before the day is out. So let's start by reviewing a little bit where we are so far. So we talked about a planning method for Markov decision processes that exploits the Bellman equation. One such algorithm was value iteration. Remember, value iteration takes the Bellman optimality equation and turns it into an update rule, and in this way iteratively refines estimates of the optimal value function that are stored in a big table. So the computational complexity of value iteration, it's quadratic in the size of the state space and linear in the size of the action space per iteration. So one iteration means doing an entire sweep of the state space. So remember, in value iteration, both policy evaluation and policy improvement are combined into a single update rule. So if I apply that update rule to every state in my state space, then I've done an iteration. And that is quadratic in the size of the state space and linear in the size of the action space. The number of iterations that I will need to do to converge is polynomial in the size of the state space, and this quantity 1 over 1 minus gamma, which is like the sum of all the weighted terms that are based on gamma. So on the one hand, this is an efficient algorithm, because if you think about a naive approach, an exhaustive approach that doesn't leverage the Bellman equation and just says, okay, let's take every possible deterministic policy and look at its value and then pick the best deterministic policy, that would be much less efficient, because there are an exponential number of deterministic policies, and yet we have a polynomial algorithm. So on the one hand, this is an efficient algorithm, and it's efficient because of this insight that underlies the Bellman equation. On the other hand, these states for whom we are trying to learn values, they are in practice typically described using features. So we might, for a given state, have a feature vector whose values together describe what the current state is. And the problem is that the size of the state space is exponential in the number of features used to describe each state. So, when you say the value iteration is polynomial in the size of the state space, this actually leads to an algorithm which is exponential in the number of features. So this is what Bellman referred to as the curse of dimensionality. So in practice, as we want to solve harder and harder problems with larger and larger state spaces that are described by more and more features, this algorithm actually performs quite poorly. And the key missing ingredient here is generalization. Because what we're doing when we apply one of these algorithms is we're learning a separate value for every state or every state action pair, with no attempt to generalize across states or state action pairs. So generalization, of course, is the entire goal of all of machine learning. So it might be a bit surprising that that generalization is a missing ingredient in a whole family of reinforcement learning algorithms that we've learned about so far. So, the reinforcement learning methods that we already talked about, like TD0 and SARSA and Q-learning, they are learning algorithms in the sense that they learn from data inductively rather than computing values deductively from a model, like their planning analogs do. But the kind of learning that they do is quite simplistic in the sense that you're estimating a quantity by computing a sample average from some data. So it's learning in the sense that you're generalizing from data, but there's no generalization in the sense of generalizing across states or across state action pairs. So the generalization that you do is just, to estimate some expectation given a bunch of samples drawn from that particular state or state action pair. So we will need to do better if we want to build practical algorithms. So as I mentioned, these reinforcement learning algorithms that we already discussed, they can exploit the Bellman equation without needing a model, and they have typically much weaker guarantees. So, whereas value iteration is an algorithm that requires only computational resources and only polynomial computational resources at that, these learning algorithms, they require not just computation, but they require data. And typically, we can only say something about what they learn in the limit. So these model-free algorithms, they're guaranteed to converge to the optimal policy in the limit. If some conditions are satisfied, we have a finite state and action space. We have this condition which is sometimes called greedy in the limit with infinite exploration, which ensures that we visit every state action pair often enough to learn properly about it, but that in the limit we're going to stop learning and exploring so that we can actually converge to the optimal policy. And some other details like gamma needs to be strictly less than 1 and we need to have finite variance. So saying that an algorithm will find the right answer in the limit is not that useful in practice. And these algorithms, like Q-learning and StarStat, they are massively data inefficient. If you think about it for a minute, the way these algorithms work is they take a data stream which is coming from the real world, which is like a very precious, priceless source of information, because gathering data by interacting with the real world is both expensive and dangerous. So the cost of obtaining this data is very high. And what do these algorithms do with this data? They take each data point as it comes in, they use that data point to form one update, and then they throw the data away. So this is massively data inefficient. So if we're going to do better, if we're going to actually build practical algorithms for reinforcement learning, we're going to need to fill in some missing ingredients. I already mentioned generalization across states and actions. Data reuse, so instead of throwing the data away after one update, we're going to have to find ways to reuse it, to either replay the data or to build models from the data that incorporate all the data that we've seen. And we're going to need to do smart exploration. If we're interacting with some big complex state space, we're going to need to be really clever about what data we obtain so as to minimize the amount of data that we need to get a handle on that complex task. So the first of these three, generalization, is basically the focus of today's lecture. Function approximation is going to enable us to generalize across states and actions. Data reuse, we will get to that a little bit when we talk about deep RL. Smart exploration is unfortunately mostly beyond the scope of this introduction. Okay, so let's talk about generalization. So to achieve this generalization, we're going to need to replace this table with some kind of function approximation. So our value function won't be represented by a table, it will instead be represented by some parametric function, which will have some weights, and the number of weights will typically be much less than the number of states. And then by fitting these weights, we will come to an approximation of our value function. So to start with, we can just again think about policy evaluation. We have some arbitrary policy pi. We're trying to estimate its value, but instead of doing so by filling in a table, we're going to do it by fitting some weights to a parametric approximation of that value function. Okay, so what is the objective that we try to optimize in order to fit this value function? Well, we can just try to minimize the mean squared error. So that's what's shown here. We want to find the setting of these weights that minimizes the mean squared error across all states. And for each state, we're going to weight it by what's called the on-policy distribution. So this is basically the probability of the state being visited by the policy pi, whose value function we're trying to estimate. And then for each of these states, we just here have mean squared error. This is the true value function, and this is our approximation to the value function. So this is very straightforward, especially if you have any experience with supervised learning. But there is actually already here kind of a big idea, a key idea, which is that all the algorithms that we've already learned about for reinforcement learning, we don't need to think of them as entirely separate from the rest of machine learning. Instead, we can think of function approximation as a way to reduce reinforcement learning to a supervised learning problem. So once I had this formulation here, with this parametric representation of my value function and this loss function to minimize, I can use all of my favorite machine learning tools. So I can represent this value function with a decision tree or a neural network or support vector machine or whatever you like, and I can use all my tricks from supervised learning to perform this policy evaluation task that's crucial to reinforcement learning. However, as we will see as today's lecture goes on, the story is not so simple, and there are some significant difficulties with this reduction. So we've reduced policy evaluation to a supervised learning problem. However, it's not exactly like the supervised learning problems we typically see. So it's an active problem. So again, the agent has some control over the data that is collected. So we're not just doing supervised learning on some fixed data set. It's an incremental learning problem because the data is coming in bit by bit. We don't have some fixed data set given to us in advance. And perhaps the most significant problem, it's a non-stationary one. And there are multiple sources of non-stationarity here. So this will become clearer as we go on, but just to give you a hint now. In this loss function, there's an important term in this loss function that I'm not actually able to compute. And it's this one, the true value function. I don't know the true value function, so I'm not able to to actually compute and minimize this loss. So I'm going to have to replace this with some kind of estimate. And this estimate will itself be changing over time, which will prove to be a crucial source of non-stationarity. And of course, at the end of the day, I'm not just interested in policy evaluation. I'm interested in solving the control problem. I want to find a good policy, which means when I do policy evaluation, I'll be doing policy evaluation on a policy that is itself changing over time because I'm going to use the result of policy evaluation to do policy improvement. So when I try to minimize this mean squared error, I'll be trying to track a moving target because the value function that I'm trying to estimate will be changing over time as the underlying policy itself changes. So these turn out to be significant complications in performing function approximation for reinforcement learning. Yeah? If mu s is 1, then s is the only state the policy will ever visit. So that would be a pretty unusual setting. Then
yes. So that we are just wondering why we are not
So what would you propose instead?
So it's not a policy.
It's not what?
It's not a policy.
Not a policy. So this is policy evaluation. So we just have some fixed policy pi. We want to estimate its value function. Mean squared error is not the only loss you could minimize, but it's a reasonable one. It's used throughout supervised learning. I don't see any particular reason to object to it. So what distribution you should use here to weight the mean squared error, that can sometimes be a subject of debate, in particular if you're learning off policy, then there can be a question there as to what the right distribution is. But if we're trying to just do policy evaluation for some fixed policy, then the distribution of states induced by that policy seems like quite a reasonable choice. No, this is just policy evaluation. Right. Any other questions? Right, so these difficulties in reducing reinforcement learning to a supervised problem were some of the biggest obstacles to making reinforcement learning work in practice, and that held back the field for quite a while. And so deep reinforcement learning was a big breakthrough, mainly because it overcame these difficulties, at least in practice, if not in theory. Okay. So let's suppose we want to minimize this mean squared error, and we're going to do that using our favorite tool, stochastic gradient descent. So this leads to an update rule, where we have our old weights, and we're going to compute our new weights by taking a step in the direction of the gradient that will reduce this mean squared error. Okay, so now if I actually compute this gradient using the chain rule, I get this update rule that looks like this. This is my error term, and this is the gradient now of the value function with respect to the parameter w that I'm optimizing. Okay, but now here comes the difficulty. I'm not able to perform this update because this update has a term in it here, the true value function, which I don't know. That's actually the thing that I'm trying to estimate. So the simplest thing that I could do here is, again, use Monte Carlo methods. So I just replace this value function, which I don't know, with a sample return. So I was in state st, and I interacted with the world for an entire episode. At the end of the episode, I'm going to observe how much return I accrued. That's my sample return. So I just replace this with the sample return, and this is now my update rule. Okay? So now I have an algorithm which can incrementally optimize an estimate of the value function, given only data, given only samples generated by interacting with the world using that policy. And it will converge to a local minimum. So I'm just doing stochastic gradient descent, so I'll travel to some local minimum. And in fact, I can use not just the sample return here, I can use any unbiased target that I want, and I will converge to a local minimum. As long as the quantity that I use here is an unbiased estimate of the true value of the policy for that state, I will converge to a local optimum. Okay, now as we saw yesterday, Monte Carlo methods, the downside of them is that they're very data inefficient because they don't exploit the Bellman equation. There's no bootstrapping. So what we would like to do now is replace that sample return with something that bootstraps. So we would like to have a function approximation variant of TD0. So we can do that in the following way. We just take the update rule we saw on the previous slide. We replace the sample return with this quantity in red, a sample reward, plus a discounted bootstrapping off the value of the next state. So this quantity here is obtained by querying my, my function approximator, my estimate of the value function, for the subsequent state. Okay, now here's the key concept that underlies most function approximation methods for reinforcement learning, and it's called semi-gradient. So in this approach, everything in red here, we treat as a constant. So just like here, if we magically knew the value function, or if we use the sample return, those targets are the things that we're regressing towards. We treat them as constants. And that was fine in those cases because they actually were constant. Here, it's not constant because this term itself depends on WT. But we're going to ignore that dependence and treat it as if it was a constant. Okay. And this is going to give us an algorithm which still converges, at least in the linear case. Now there are methods that don't take this shortcut, that are so-called true gradient methods. The earliest example of this is from Baird, who in '95 he proposed a residual gradients, which is you get an update rule that's shown here. It's exactly the update rule that you would get if you actually computed the gradient. So if we go back here, this thing here, the gradient of the mean squared error with respect to the weights, if you actually just compute that gradient where here you have a TD0, you don't get this here, you get this. And this thing includes this extra term here, and this extra term arose because of the dependence of the mean squared error through the target on WT. So if we choose not to ignore it, then we get this residual gradient method with this extra term. Unfortunately, these true gradient methods, they learn very slowly. And there are a lot of papers talking about these kind of methods and how they can be sped up and why are they slow and so on. Long story short, I think the simplest intuition can be obtained by just looking at this term here, these two terms here. So in most cases, ST and ST plus 1 will be similar. So in most cases, the agent is not going to travel to a very different state in one time step. So ST and ST plus 1 will be similar. And also, in most cases, gamma is very large. So gamma will typically be very close to 1. If those two conditions hold, then these two terms will be very similar, which means this term will be very close to 0. which means the gradient will be very close to 0, which will cause learning to be very slow. Of course, you could just increase the learning rate, but then you'll have very high variance and it will be very hard to learn. So in practice, these semi-gradient methods are completely dominant. Nobody uses these residual gradient methods in practice except in a few very unusual special cases. Okay. Let's look a little bit more closely at the linear case. As always, this is a very important special case and is very useful for understanding how things work in general. So let's suppose our state is described by this feature vector. So for some state, we get this vector of features describing the state. And then our weight vector, so our value estimate for some given state, is just the inner product of that weight vector with the feature vector. Okay? In this case, the gradient term just becomes the feature vector itself, and our TD0 update rule reduces to the following, what's shown here. This is just like the update rule we saw before, but now the gradient term is just the feature vector itself. So because we're doing linear function approximation, we have the nice property that if we converge to a local optimum, that local optimum will also be the global optimum, thanks to the reliance on linear function approximation. However, because we're using semi-gradient methods, we actually won't converge to the local optimum. We will converge to something else called the TD fixed point. And the TD fixed point, fortunately, is in practice typically near the local and therefore the global optimum in the linear case. So what is the TD fixed point? Let's look at this a bit more closely. So let's rearrange our update rules. So what we have here is just our TD0 update rule for the linear special case. So the gradient here has been replaced by the feature vector. And where I've just replaced anything that had v in it, I've replaced it by the inner product that is used to estimate v. Okay, so this line here looks exactly like this thing here, but just the v's have been replaced by the inner products that are equal to v. Okay. Now I just rearrange some terms. I just group things differently, such that everything is I just distribute the x, and then I group everything that has a WT term into it, and that allows me to write the expected weight vector. So I'm doing stochastic gradient descent here, right? So I have some sample. I was in some state. I got some sample reward and some sample next state, and then I use that to perform an update. So now we can ask ourselves, what would the expected update be? So if I were to do from this given state, if I were to generate many sample rewards and next states and perform all those updates, what would the average update look like? So the expected new weight vector given the old weight vector can be written in the following way as the original weight vector plus the difference between this vector and this matrix times our weight vector. And what is this matrix? It's just the expected, it's just the expected value of this term from our update. And what is this vector? It's just the expected value of this term in our update. Okay? So we can separate our update into these two quantities involving A and B and then write it in this nice form. Now, we can use this rearranging to analyze what the TD fixed point is. So if we have converged, suppose we're doing this semi-gradient method with this linear function approximation, we're updating, and then we reach convergence. If we have converged, then that implies that the expected update is 0. So let's see. This is our expected update, right? So if the expected update is 0, that means this quantity must be 0, right? So the expected update is 0, that means this thing is 0. Now we take this thing and we just solve for W. And if we solve for W, we get the TD fixed point. So when the semi-gradient method with linear function approximation converges, this is what it will converge to. Okay? So it's not the local minimum, it's something else called the TD fixed point. Now theoretically, we can analyze the relationship between the TD fixed point and the local minimum, and that's what's shown in this equation. So the mean squared error at the TD fixed point is bounded by this expression that's a function of the mean squared error at the local optimum. So that's nice, the error is bounded. However, this bound is actually quite loose because of this term here. So remember, gamma is typically close to 1. So this number is typically very large. So this is quite a loose bound. So this theoretical result is actually not that helpful. What is helpful, though, is that in practice, the TD fixed point is typically very good. It's typically one with very low error. So that's why semi-gradient methods are quite useful in practice. They learn really fast, much faster than true gradient methods, and they get you they converge to a point which has low error in practice. So a question you might be asking is, if in the case that we're doing linear function approximation, if we can analyze it in terms of these matrices and vectors, do we need to take an iterative approach at all? Do we need to use stochastic gradient descent to incrementally reach the TD fixed point, or can we just directly compute the TD fixed point? So this, excuse me. So this is the idea behind least squares temporal difference methods, and a whole family of reinforcement learning methods that are based on this principle. And so the idea is as follows. Rather than using our data to incrementally perform a bunch of stochastic gradient descent, we're going to use our data to directly estimate the matrix A and the vector B. Then if we can invert that matrix, we can just directly compute the TD fixed point. Okay? So the result of the least squares temporal difference method will be these weights, and they'll just be inverting the matrix and multiplying it by the vector. And the matrix and the vector will be computed from data by just summing up what the corresponding terms would be for each of the data points in our data set. So we have some episode of data starting at time step 0 and going to t minus 1. For each of them, we can compute this term. We add up all those terms. That's our estimate of the matrix. We do the same thing for the corresponding term to get an estimate of B. Right, so if we do what's actually shown here, then the cost of computing A and B is going to depend on the amount of data we have. It's going to depend on the number of time steps in the episode. But of course, we can update them incrementally, so every time we get a new data point, we just update our estimate of the matrix and the vector. That, of course, still leaves us with the matrix inversion step, and generally inverting a matrix is cubic in the number of dimensions. But this is a special matrix because note this matrix is constructed by summing up a bunch of outer products. And this kind of matrix can be inverted in quadratic time using something called the Sherman-Morrison formula. So these approaches are still expensive because the cost is quadratic, not linear, but it's not as bad as you might have feared. Yeah. Sorry? Yeah, that's a good point. It might not be. So that will depend on some linear independence properties among the features. So that's a good point. That doesn't always hold, and that's what this term here is for. But yeah, that can be an issue. Yeah, good point. Yeah. Sorry, say again. Doing what? Oh, good question. The question is, would it be a good idea to do semi-gradient methods till you converge to the TD fixed point, and then do true gradient methods to get to the local optimum? I don't know. It sounds like a good idea to me. I can't think of any example of anyone doing that. So possibly it doesn't work for a reason I'm not aware of, but it sounds like a good idea. It would be slow, of course, the true gradient part, but it could be worth it in some cases. Other questions? Yeah. Yeah, so if I understand correctly, you're saying you don't need to invert a new matrix every time. Yeah, that's true too. Yeah, absolutely. Okay. Okay, let's move on to nonlinear function approximation. Of course, the main topic of interest here is function approximation with neural networks. So, you know, in the simplest setup, the features that describe the state space are the inputs to our neural network. And, you know, if we're just doing, you know, so far we're just considering policy evaluation, so we're just trying to estimate, you know, V pi, then our network can have a single output, which is just corresponds to that value estimate. So this is an approach that had some quite early success. People got quite excited about function approximation for reinforcement learning in general, and function approximation with neural networks in particular. And the sort of most famous iconic success of this was Jerry Tessaro's TD-Gammon system, which used neural network function approximation together with a temporal difference learning to teach a computer to play backgammon with really extraordinary success, playing at a world-class level. So he had a number of different versions of the system which differed basically in how clever the feature engineering was. So the initial system used really just like raw input describing the board, and then he developed more sophisticated features, and those resulted in significant improvements in performance. Then later, after the deep learning revolution happened, he went back and got rid of all the feature engineering and went back to the raw features, but just used all the newly available horsepower to train a much larger neural network, and he was able to match the performance of the networks that used feature engineering. So he was just kind of ahead of his time in the sense that there weren't compute resources and sort of, you know, deep learning tricks to train large neural networks at the time. So his approach used something that's called afterstates, which is a technique that is useful in some specific settings where you have what I would call a partial model. So if you think about backgammon, you know, you're playing against some fixed opponent. So actually he did self-play, so he was playing against his own agent, but we can sort of ignore that issue for simplicity. Imagine you're just learning to play against some fixed opponent. So the opponent is part of the world. So if you formulate this as a Markov decision process, you know, a state corresponds to a board position. When you take an action, the transition involves, you know, you moving a piece on the board, the other player acting, and then control comes back to you. So the transition function involves these two steps: you changing the board directly as a result of your action, and then the other player acting, and only then do you get to act again. So the key observation here is that the first part of this transition function is known and the other part isn't. So, you know, just by knowing the rules of backgammon, I know if I take this action, what the board will look like after I take that action. There'll be a new piece on the board, or this piece will have moved to that location, right? So that part of the transition function is trivial. The other part, what the other guy's going to do, you don't know. So that's why we have a learning problem, because we have to interact with this unknown environment. So the idea behind afterstates is not to train a value function to represent the value of the state when it's your turn to act, but to represent the value of the state in between, you know, in between these two parts of the transition function. So after you have acted, and the consequences of your action have already been represented in the board state, but before the opponent has acted. So this is easier to learn because, you know, you can imagine there could be many different board states which, after you take an action, yield the same new position, and you want those to be treated the same by your function approximator. So this is what the output of the TD-Gammon network actually represent. So the reward function is just 1 if you win the game and 0 if you lose. So the value function corresponds to the probability of winning the game from the after state that results from the move that you've just taken. So then to select actions, you have to look at all your actions, use your partial model to figure out what after state they would bring you to, query your neural network for the value of those after states, and then select the action whose corresponding after state has the largest value. So this was a huge success and got people really optimistic, but it turned out to be really difficult to replicate this success in other domains. There's actually a fair amount of research been done about what is it about backgammon that makes it friendly to nonlinear function approximation and reinforcement learning. And some people have even tried to figure out how we can take other problems that aren't friendly to nonlinear function approximation and backgammonize them so that they are sort of transformed into a problem that where this scheme that Tesaro had so much success with can be replicated. Okay, so that's, how am I doing on time? 10 minutes. Okay, we'll do a few more slides and then stop for lunch. So everything we've talked about so far was function approximation for policy evaluation. We're trying to estimate the value of some fixed policy. Of course, what we'd really like to do is control. So we would like to estimate the optimal value function using our function approximator. So conceptually, the step is very straightforward from what we've seen already. We just have our parameters W. They're going to parameterize a Q function instead of just a value function. And we can write down a semi-gradient version of the Sarsa algorithm. So here we have the Sarsa update rule, where we're comparing our estimate of the Q function to a target built by bootstrapping off of that same Q function. And then here we're going to have this gradient, the gradient of the Q function with respect to the parameters W. And again, this is a semi-gradient method because just like before, we're ignoring the dependence of the Q function on W in this term. So if we, this is going to, so both the TD method and the Sarsa method, they're both going to allow us to deal with continuous states because, we can generalize across states. So the fact that there's an uncountable number of states poses no particular difficulty. We still don't have a way to deal with continuous actions because although we could, represent the value in a problem where the action space was continuous using this same kind of parametric model, what we don't know how to do is policy improvement or action selection. If we have a continuous action space, then maximizing with respect to the action space is itself a hard optimization problem, and the tools we've learned about so far will not get us there. But in the next lecture, which will start either at the end of today or tomorrow, we will talk about policy gradient methods, and policy gradient methods are designed to tackle exactly this difficulty. But for now, we can cope with continuous states, but not continuous actions. Okay, so if we want to do control with a nonlinear function approximator like a neural network, then the sort of canonical thing to do is, again, we have one input for every one of our state features, but now instead of having one output, we have one output for each available action. So, you don't have to do it this way. You could put all the state features on the input, and then you could also on the input have the action or some features describing the action, and then you would again have a network with one output, just like we had, in TD Gammon with just value function approximation. The downside there is that for every action, you would need to do a separate forward propagation of the network. Whereas with this architecture where you have one output head for every action, in a single forward pass, you can compute all the Q values that you will need to do policy improvement or to do action selection. Because you can just take a max over all the outputs of the network in order to figure out what the maximizing action is. Okay, when we want to do off-policy learning, so remember Sarsa is a control method, but it learns on policy, so we're learning about the policy that's used to gather the data. If we want to go off policy, then things become more complicated. So there are sort of two naive approaches. We can take our semi-gradient temporal difference method and make it off policy by just adding in an important sampling correction here. This is just like what we did yesterday with the Monte Carlo methods. So, the data is being gathered from some policy pi prime, but we are trying to estimate the value of another policy pi. So this importance ratio ensures that our estimates are unbiased. Similarly with Q-learning, we can take our Q-learning method, we can take Q-learning, which is by nature off policy, and we can turn it into a semi-gradient method. This is just the Q-learning update rule. It's just like the Sarsa one, but we have this maximization here. And again, we have the gradient of Q with respect to W. We don't have any importance sampling in this update rule. Now, yesterday we had a whole discussion about why we don't need importance sampling when we do Q-learning, but that argument actually holds only in the tabular case. If we're doing function approximation with Q-learning, in principle, we really should do importance sampling even for Q-learning. Because the mean squared error, remember, is weighted according to the on-policy distribution. So we would, let's go back to that. Here, we define the mean squared error with respect to the on-policy distribution. But now the data is being gathered with respect to some other policy. So that discrepancy gives rise to a need for importance sampling. And there has been a lot of effort to develop off-policy Q-learning methods with function approximation that do this importance sampling in a proper way and actually can learn in a useful way. But I would say this success there is mixed at best. And in practice, what people do with semi-gradient Q-learning methods is just ignore the need for importance sampling. But both of these methods are known to be vulnerable to divergence. And this is the first hint that we have about some of the difficulties of doing function approximation and reinforcement learning and why it isn't as simple as just applying your favorite supervised learning methods to the problem. Right, so I think this is a good place to stop. When we come back later today, we'll look at why that is, why that divergence arises, and what can be done about it to build deep reinforcement learning methods that are actually useful in practice. So I will see you guys again later this afternoon. Enjoy your lunch. Welcome back, everyone, to the second part of this lecture on function approximation and deep reinforcement learning. So what we covered before lunch was basically starting from the tabular methods, introducing the notion of a parametric approximation to our value function, doing that in policy evaluation, and doing it in for control to actually estimate the optimal value function in an on-policy setting. And then this is the slide that we were looking at when we ran out of time, which is about off-policy function approximation. So for TD0, we can make it off-policy just by introducing these importance weights, just like we did in the Monte Carlo setting. For Q-learning, we can just take the Q-learning update rule and add this gradient using the semi-gradient update rule that we've seen in the other contexts. Strictly speaking, we should do importance sampling here, although in practice, typically we don't. So this is a simple approach to off-policy function approximation, but both of these methods are known to be vulnerable to divergence. And this is something that people started to realize in the mid-90s, basically at the same time that Tessaro was having great success with backgammon and people started trying to replicate that success in other domains. That's when people started to realize, hey, there's a non-trivial problem to be solved here in doing function approximation and reinforcement learning. It's fundamentally more difficult than it is in supervised learning. And this was first crystallized by Baird, who had this counterexample that showed how off-policy function approximation can go wrong. I mention it here just because he was the first to come up with a counterexample, but I find this counterexample too complicated and confusing. So what I would like to do instead is discuss a simpler counterexample which was proposed later by Tsitsiklis and Van Rooij, and which is really nice and simple. So the situation is described in this figure. We have a world in which there are two states. So this is state 1 and this is state 2. And we have a parametric representation of our value function, which is what's shown here. So we have one weight, so it's just a scalar parameter, and it is multiplied by a feature vector, and the feature vector is just the index of the state. So in other words, our value function estimates v of state 1 as w and v of state 2 as 2w. So that's just sort of an arbitrary parameterization of the value function for this MDP with two states. And these arrows show the transition probabilities from state 1, you go to state 2. From state 2, you either return back to state 2 or or the episode terminates. Now, in this MDP, there is no reward to be had. The reward function is 0 everywhere. So the true value function, of course, is 0, which means the optimal value of W is also 0. Okay, now let's suppose we learn off policy using a sampling distribution which visits only state 1. Okay, then let's take a look at what our updates will look like. So let's go back to the previous slide for a second. Where have we got? Didn't know it was that far back. Yeah. Okay, so our error term is going to be based on this target, which is the reward plus the discounted value of the next state minus our current estimate of the current state. So back to our example, we're updating only from this state, and the reward will be 0. The discounted value of the next state will be gamma times 2W, and our current estimate of the value of the current state will be W. So this is what our TD error will look like, and our change to W will be proportional to that TD error. So what you can clearly see is that for any gamma that's greater than 0.5, this quantity will be positive, meaning that the weight will increase. So every time we perform an update, we'll be increasing the value of W. This process will never end, and W will diverge. Remember, the true value of W star is equal to 0, and yet W will be increasing. Of course, this is quite an extreme example, because how would you expect to learn the value function if you only visit state 1? Wouldn't you expect to at least need to have some data from state 2 in order to have any hope of learning the value function, regardless of what algorithm you're using? But it turns out even if you have uniform updates between state 1 and state 2, you can still get this same divergence for a large enough gamma. So this is a fundamental problem. Obviously, we would like to have reinforcement learning algorithms that converge. If we're going to do function approximation, we might be willing to content ourselves with local minima, but we would at least like to converge to those local minima. Divergence is not something that we are happy with. So that's kind of like a simple example that illustrates mathematically how this can occur. In practice, people started to notice this in some sort of toy benchmark problems that at the time a lot of reinforcement learning papers used as empirical test beds, the most overused of which is a mountain car. It's like the MNIST of reinforcement learning. So it's a simple problem in which you have a two-dimensional continuous state space, and you have that describes this car. It's an underpowered car that's trying to get to the top of this hill. Because its engine isn't big enough, it can't just drive up the hill, so it has to learn to go backwards up the hill behind it to build enough momentum to get to the top of the hill. This problem is not very hard to solve with reinforcement learning, but it does require the right technique. And Boyan and Moore had a paper in '95 where they showed that Q-learning, together with nonlinear function approximation, fails on this simple problem. So this was an early paper that was kind of raising the alarm bells about function approximation and reinforcement learning. And Rich Sutton, who is kind of an evangelist for reinforcement learning and was trying to convince everyone reinforcement learning was the path forward for AI, he understandably felt a bit threatened by this negative result. So he responded the next year with a paper which showed you can solve a mountain car with function approximation, but he used SARSA, and he used a linear function approximator called tile coding. So on the one hand, he reassured people that these kind of problems can be solved with function approximation and reinforcement learning. At the same time, the difficulties with Q-learning in particular and nonlinear function approximation remained unresolved. But as a result of that, this tile coding approach became quite a popular representation for function approximation before they were supplanted by deep neural networks. So the idea behind the tile coding, it's like an ensemble of discretizations. So if you have a continuous state space, say X and Y, and a simple way to do function approximation is to just discretize that continuous space. So you just take a grid, and then any state that falls in a certain cell in the grid, it shares its value function with the other states that fall in that cell. So of course this gives you a very coarse approximation. So one way to make the approximation finer is to make the cells in the discretization smaller. But if you do that, then you reduce the amount of generalization that you can perform. So the generalization happens only within a cell, so the finer your discretization, the less generalization you have, the more data you will need to learn. So tile coding is a way of getting kind of the best of both worlds. So you have not just one discretization, but a bunch of discretizations, and they're all offset from each other by some small amount, typically randomly. Then, when you're in a certain state, the feature representation of that state is basically a bunch of binary features indicating which cell in each tiling is activated by that state. So here we have this state X, and there's one tiling here in which that state X activates this square here, and there's a second tiling in which that same X activates this other one. And then the value function will be a linear function of the features activated by the current state. So you basically take a low-dimensional problem, with like continuous real-valued features and turn it into a high-dimensional problem with binary features. And in this high-dimensional space, you hope there will be a good linear function which approximates your value function. So this is successful on the kind of problems like mountain car that people were struggling with at the time. However, as you can imagine, this scales very poorly. If you have a high-dimensional state space, then constructing this tile coding and learning in it becomes totally intractable. So this was kind of a short-term solution to the difficulties that people were facing. Since then, there's been a huge amount of research into function approximation and reinforcement learning, trying to analyze why this divergence occurs, trying to develop algorithms that don't suffer from this divergence, both empirically and theoretically. Sutton himself has dedicated a huge amount of effort to this problem, and the more recent true gradient methods that don't use semi-gradients but that use true gradients that have come after Baird's original true gradient method. Many of them were developed by Sutton and collaborators of his, and theoretically they made a lot of progress in that they were able to develop methods that do nonlinear off-policy function approximation and still converge, but empirically these methods are not useful. They still learn much too slowly, and these convergence guarantees have restrictive assumptions that they depend on. So in the new second edition version of the Sutton and Bartow textbook, they kind of summarize the take-home message of all of this research in what people are now calling the deadly triad. So these are like the three ingredients that, if they are all present at once in your reinforcement learning system, can give rise to this problem of divergence. So the first one is function approximation. With tabular methods, we don't have any of these problems. We have great methods for the tabular setting. The second one is bootstrapping. If we just do Monte Carlo instead of temporal difference methods, these problems also go away. And the third one is off-policy learning. So if we just would restrict ourselves to SARSA and temporal and TD methods without doing things like Q-learning, we can also avoid these difficulties. So a key question then is, how important are these three elements? Do we need these three elements? If we imagine all this research is aiming towards some magical, amazing reinforcement learning algorithm that's going to solve a wide range of problems for us, how committed are we to these ingredients being in that algorithm? Or do we see a path to building that algorithm without some of these ingredients? Because if these ingredients together cause divergence and we need all these ingredients for our dream algorithm, then we have a problem. So we can decide for ourselves. Sorry, let's answer this question first. So function approximation, this is all just my personal opinion now. Function approximation, you can't live without it, I think. Tabular methods are not going to solve interesting real-world problems except in a few very isolated cases. Generalization across states and state action pairs, absolutely essential to reinforcement learning in the same way that generalization is key in any other area of machine learning. Bootstrapping, essential is maybe a strong word because we can learn with Monte Carlo methods, but if we're going to make reinforcement learning algorithms practical, they're going to need to be sample efficient, and even the best algorithms are not as sample efficient as they need to be. And there's a lot of evidence that shows that temporal difference methods are more sample efficient than Monte Carlo methods. And as I mentioned before, when you use eligibility traces, you have this lambda parameter, which allows you to smoothly interpolate between Monte Carlo and temporal difference methods. And basically every empirical analysis that has been done of this lambda parameter finds that the best setting of this parameter is not 0 or 1, but somewhere in the middle. Typically much closer to 1 than to 0, but crucially not 0 or 1. So that suggests that we will need bootstrapping if we want to learn in a sample efficient way. And also, intuitively, bootstrapping is the algorithmic codification of Bellman's great insights of the Bellman equation. And it seems unlikely that going forward, the right algorithmic approach will be ignoring that insight. So probably bootstrapping is, if not essential, very important. The third one, off-policy learning, most debatable. Off-policy learning is certainly nice, you know, if we're going to have a great reinforcement learning algorithm, that algorithm is going to need to explore in a smart and efficient way. So given that that exploration is key, it would be nice to be able to learn off policy so that we can learn about a policy that is not explore while we're doing the exploration. That's the most common application of off-policy methods, is to learn about a greedy policy using data gathered from an exploratory policy. But still, that's a nice feature. We could do something not quite as good, but still pretty nice with Sarsa-like methods. You explore in order to gather sufficient data. You learn about the exploratory policy, but you anneal the exploration over time such that in the long run you do learn a greedy policy. Yeah, maybe there's an annealing schedule that you need to fine-tune, and maybe that's a bit of a headache, but it's not really a fatal problem. So Sutton makes a stronger argument for off-policy learning, which the merits of which are debatable. So his position is that actually the only way to be sample efficient is to learn many, many things at the same time. So as some of you may know, the idea of like auxiliary loss functions, auxiliary tasks has become very popular in machine learning and deep learning. If you have a task where you have only a small amount of data, you can train your neural network to solve a similar task on which you have a lot of labeled data, and then bootstrap from there to the task that you actually care about. This idea has been ported to reinforcement learning. DeepMind has some papers to this effect where you have a reinforcement learning task where the reward is quite sparse, but at the same time that you learn to maximize that reward, you can also learn to solve a bunch of other tasks like, let me figure out how to elicit some changes in the environment, or let me learn how to predict some visual features in the environment, things that are not the task itself, but are related to the task. And in solving that task, you speed your ability to learn the main task. Sutton himself had this thing called the Horde framework, which was all about unsupervised, like a robot exploring an environment in an unsupervised way and learning to solve thousands of prediction problems along the way, or positing, I don't know what my reward function is because I've never experienced any reward, but I can posit 1,000 different reward functions that might exist and learn value functions for all of them. And the sort of interaction between that learning will lead to some sample efficiency. None of this is possible without off-policy learning, because if you're solving multiple tasks at the same time, the policy that you're executing can only be optimal for at most one of those tasks. It can only be a greedy policy with respect to one of the value functions you're estimating. So if you buy into that paradigm, if you buy into that being the way forward for sample efficiency for reinforcement learning, then arguably off-policy learning is a crucial tool. It's important to note what is not in the deadly triad. So first of all, control is not in the deadly triad. If we're just doing policy evaluation, we can still experience this divergence as long as the policy evaluation uses function approximation, bootstrapping, and is off policy. Learning is also not in the triad. So we may not be doing reinforcement learning at all. We could be doing sample-based planning. Suppose you have a model, so you're doing not reinforcement learning but dynamic programming, but you're doing dynamic programming on a really large state space, so you don't want to use a tabular representation of your policy and value function, so you're using function approximation. Then you can still have this divergence as long as the three elements of the deadly triad are there. No learning involved, no learning or data involved. Nonlinearity is also not in the triad. So this is not a problem that's specific to neural networks. We can experience divergence using linear function approximation, again, as long as we're bootstrapping and doing off policy all at the same time. Okay, so, this leaves us in a bit of an unsatisfying situation because we have some theoretical methods that have some nice convergence guarantees, but they're totally useless in practice. And in practice, we have this divergence problem. So how has this problem been cracked? The answer is maybe a little bit underwhelming. It's no single thing. It's no great theoretical insight. It's kind of an accumulation of a lot of small things put together in exactly the right way. And it's that sort of accretion of small developments which, at a certain moment led to this explosion of deep reinforcement learning and this great success. So what I want to do is sort of present to you the canonical, the deep Q-learning algorithm, the canonical algorithm of deep reinforcement learning, which sort of in practice overcomes these difficulties. But before doing that, I want to give a bit of historical context, because most of the ideas that exist in that algorithm are actually quite old, and it's useful to understand those ideas first and then see how they've been assembled into this algorithm that works amazingly well. So the first of these ideas is something called experience replay. So this concept is a bit out of place in this lecture, because really this concept is related to something called model-based reinforcement learning, which comes in the second half of tomorrow's lecture, and which actually, to be honest, we probably won't get to at all. But basically, experience replay is a way to be data efficient by reusing data. So the philosophy behind model-based reinforcement learning is, instead of taking our data and using it once to update some estimate of the value function of the policy, we're going to take our data and use it to estimate a model. Once we have a model, we can use decision theoretic planning to compute a value function and policy, just like we did with the dynamic programming methods we talked about on day one. So as new data comes in, we update our model, and we're always planning with respect to a model that takes into account all the data we've ever seen. So there's no throwing away of data like you have in these naive model-free methods. Of course, models are very difficult to learn, and getting the models to generalize properly is a huge headache. In deep reinforcement learning, model-based RL is still, roughly speaking, an unsolved problem. So experience replay is kind of like a poor man's model. It's like a very simple way of getting data efficiency without actually having to build a model that generalizes well. So all you do in experience replay is every time you collect a data point, and what I mean by a data point is a tuple consisting of a state, an action, a reward, and a next state. Every time you collect a sample by interacting with the real world, you store it in a replay buffer. And then when you learn, you don't just learn from a stream of new data coming in from the actual world, you actually replay data coming from the buffer. Very simple idea. Lin proposed this back in 1992. So this requires more computation, because you could do, potentially many, for example, Q-learning updates. You could do many, many updates for each time you interact with the real world at greater computational expense, but by greatly reducing the sample complexity. So the number of samples you'll need to learn will be much lower, because you'll get a lot more learning out of each data point that you collected. So that's idea one. Idea two is something called fitted Q iteration. So this was first proposed by Ernst et al. In 2005, and then a neural variant of it was proposed by Martin Riedmiller. And this is an attempt to stabilize the learning process in function approximation so as to prevent some of these issues that cause divergence. And the philosophy here is that one of the causal factors in this divergence is the non-stationarity of the learning problem. Right? So you're trying to estimate Q star, but you don't know what Q star is, so what you're actually regressing towards is some target, but the target itself depends on Q star. So as you update Q star, you're actually changing the targets, so you're actually changing the thing that you're regressing towards. And these two things can interact in unpleasant ways that lead to this explosion of Q values and divergence. So in fitted Q iteration, the idea is to stabilize the learning process by fixing those targets for a whole learning run. So that's what's illustrated in this pseudocode, okay? So we store all our samples just like we would in experience replay. We initialize the weights of our function approximator to whatever we like. Then, on each iteration of the algorithm, what we're going to do is for each data point that we've collected, so this data point, remember, is a sample, state, action, reward, next state, we're going to construct a target. And this target, the definition of this target just depends on exactly what reinforcement learning algorithm we're using. So here we're doing fitted Q iteration, so this is like Q learning. So our target is just based on the Q learning update rule. It's a sample reward plus a discounted maximization over the value of the next state. So this target is computed using the value of these weights as they were at the moment at which we construct this data point, okay? So now, once this target is computed, it's fixed, it's frozen. We treat it now like a label for a stationary learning problem, okay? So now what's happening in this loop is here we're doing it incrementally like stochastic gradient descent, but actually this whole loop could be replaced by your favorite supervised learning algorithm. Once we fix those targets, we have a stationary, fixed supervised learning problem. So we just do a whole run of supervised learning to convergence to try to learn a value function that predicts those frozen targets. Okay, so here we're doing this with supervised learning, so this would mean, doing gradient descent to convergence, incremental updates on these fixed targets. Then only once that whole learning run completes, then we go back and say, okay, these targets are out of date, because these targets were based on some Q value estimated from some old W, but now we've just finished a whole run of updating W. So now we take the new W, recompute all these targets, and then do a whole new supervised learning run to train to the new targets. So you have the same phenomenon you had before, where the thing you're regressing towards is changing over time, but it's changing over time in these fixed intervals. And while you're doing supervised learning, you're doing supervised learning towards stationary targets. So this really stabilizes the learning process, leads to a much more effective training of function approximators at the expense of a lot of computation. So you have to do possibly many entire runs of supervised learning before you can learn a good value function. But this was a key idea. So then came the Atari learning environment. People got more interested in benchmark problems in reinforcement learning, trying to actually make these function approximators solve interesting, hard challenge problems. When the Atari learning environment was first proposed, Mike Bowling, who was one of the guys who developed it, he said, this is one of these problems that we totally cannot solve right now, but it really seems like we should be able to solve, and it shouldn't be that hard, and it should only take 5 to 10 years, so it's like a perfect challenge problem. It's beyond the state of the art, it would be a significant accomplishment, and yet, at the moment, we cannot do it at all. DeepMind took this on board and started combining some of the advances of deep learning with some of these insights from reinforcement learning, and the result was an astounding success called DQN. Unless you've been sleeping under a rock for the past few years, I'm sure you've heard about it. They trained really quite an ordinary conventional neural network to take as input, raw video screens from these Atari games, and compute as output estimates of a Q function that could be used to guide the behavior of an agent in each of these games. So they did not train one policy that plays all of these games. They trained a separate policy for each game, but crucially, that policy is trained using exactly the same algorithm with the same hyperparameters. So this was considered, so two things were significant here. One is the empirical performance of the learned behavior just blew everything else out of the water, but also the fact that the same algorithm with the same hyperparameters could be used on all these 43 games was considered a strong indication of the robustness of the learning algorithm, a robustness which had been quite difficult to achieve due to the problems in stabilizing function approximation in reinforcement learning. So how does it work? Well, once you have this background I just gave you, the idea is actually quite simple. So this is the DQN update rule. So this is really just exactly the function approximation version of Q learning, that exact update rule that we saw before, with just a couple new twists. So one twist is that here, the value, the Q value that we're trying to estimate, it's parameterized by some weights WT. So these are the value of our weights at time t, when we're performing this update. But the target that we regress towards here, this is an ordinary Q learning target, but this Q learning target is constructed using a Q function parameterized by some different weights, W minus. And what is W minus? W minus are the weights of a frozen target network. So the idea is periodically we're going to take whatever weights we have and freeze them, leave them frozen for a while, use them as W minus. So WT will continue to evolve every time we do an update, W minus will be fixed. And then, after k time steps, we'll update W minus to be the current WT. So we can think of this as a cheap approximation to neural fitted Q iteration. So the target network is changing more slowly, and it's fixed for long periods of time in order to stabilize the learning process. And the Q function that is used to estimate this target is different from the Q function that is being updated by this update. So this sort of captures some of the key elements of neural fitted Q iteration, but with avoiding the overwhelming computational expense of doing an entire supervised learning run on each iteration. So we can think of it as a cheap approximation to neural fitted Q iteration where the target network just lags behind the current weights. Now these gradients here, they are estimated from mini batches. So, and those mini batches are sampled from an experience buffer. So as the data comes in, it's put into a buffer. The buffer has a certain length. Once something gets to the back of the buffer, it drops off the end, but the buffer is pretty big. And then as we update, we sample from the buffer. We randomly sample a mini batch from the buffer, and we perform these updates. So this becomes sample efficient because we rely on this notion of experience replay. The learning is stabilized by the target network, and the result was phenomenal success, superhuman performance on the vast majority of these Atari games. So this has led to an explosion in interest in reinforcement learning in general and in deep reinforcement learning in particular. If I had a week, I couldn't possibly catalog for you all of the various extensions and bells and whistles that have been added just to the DQN algorithm alone, not to mention any of the other deep reinforcement learning algorithms that have been developed since then. So in the interest of finishing before midnight, what I've done is select a few extensions to the DQN algorithm that are possibly of particular interest to someone who might actually want to do deep reinforcement learning in practice. I did not select these myself. I let DeepMind select them for me because in 2017 they published a paper called Rainbow, and Rainbow was a paper that basically selected a number of enhancements to the DQN algorithm, put them all together, and then did like a massive empirical evaluation to see what actually helps and what doesn't. And they found that all of these contributions that are listed here were key to getting the top performance of the Rainbow algorithm. At least it was state of the art at the time in 2017. I'm sure it's been destroyed since then. So let's go through these one at a time to get a sense of where DQN has gone since the original paper was published in 2015. So the first one is the idea of double DQN, which was proposed by Hadolf and Husselt. And so this is something that he actually proposed much earlier. In 2011, he came up with the idea of double Q learning. But it was something that didn't have a big impact. It was kind of something of theoretical interest where people were like, that's interesting, but nobody really used it. But then they found a clever way to combine it with DQN, and it became quite a key tool to improve the learning process, and one which is part of the sort of standard toolkit of deep reinforcement learning today. Okay, so the idea behind double Q learning is that when we do Q learning, the maximization which appears in the update rule introduces a problem from a statistical perspective. So we're taking a maximization over these Q values, but these Q values are just estimates, right? And they're noisy estimates because those Q values were themselves estimated based on samples that were generated from some stochastic process, interaction with the MDP. So what we're doing is taking a max over a bunch of noisy estimates. And it's easy to show that this will systematically overestimate. Because, even if your data is pointing to the value being around here, because it's noisy, you'll have some samples that are large, and then when you maximize, you'll be seizing upon those statistical flukes that happen to overestimate, and that will yield a bias. So, imagine you take a maximization over a bunch of those actions, and some of those actions happen to be overestimated because of these random fluctuations. Well, you're going to be biased towards those actions. So it turns out to be not possible to totally eliminate this bias. That's something that Haddo's theoretical work has shown. However, you can reduce this bias, and one way to reduce it is to separate estimation from maximization. So the way to understand this is to start by rewriting the maximization that appears in the Q-learning update rule. So remember, in Q-learning, we've got here, this is our target in Q-learning. It's a sample reward plus a discounted maximization over Q values, okay? So we just look at this maximization part of the target. We can rewrite this maximization in a funny way. So that's what the right-hand side of this equation does. Is the right-hand side is saying exactly the same thing as the left-hand side, just in a funny way. So we can say, actually, what we're doing when we perform a maximization is we're first performing an argmax, and then we're taking the action which won that argmax, and we're looking up its value. So we can just think of max as querying the value of the thing that won the argmax. Okay? But by separating it out in this funny way, what we see is that the weights appear twice. So the weights are used once to decide the values of each action when performing the argmax, and then the weights are used again to look up the value of the action that won the argmax. And the idea behind double Q-learning is that these two weights don't need to be the same, and that by making them different, we can reduce this bias that results from taking a maximization of noisy Q estimates. So in double Q-learning, the idea was you would take your data and you would split it in half. And you train one network with one half of the data set and another network with the other half of the data set. And then when you perform updates, you would use this trick that I just described. When you computed Q-learning targets, the value would be computed with one set of weights and the argmax would be performed with another set of weights. Now, this was the idea behind double Q-learning. And in some toy examples, Hato was able to show that this reduces this overestimation and improves performance. But of course, it's very unsatisfying to have to divide the data into two halves. You're doubling your sample complexity. That's not very nice. So kind of the key insight here was that if we take this idea of double Q-learning and put it inside a DQN, we have this happy synergy, which is that in DQN, we already built this separate target network anyway. So we had these old-fashioned weights, these W minus weights that were frozen. We had that anyway in order to stabilize the function approximation. So we can just use those weights as the other set of weights that we need in order to do double Q-learning. So in double DQN, we don't have two totally separate set of weights trained on different data sets. We just have one set based on the most recent data and the target weights that are a little bit behind. And that turns out to be enough of a difference to reduce this overestimation and significantly improve the performance of DQN. So this is what the update rule, or what the target looks like. So when we perform the argmax, we use the Q values based on the current weights. So we select the action that is best according to our current weights. But then when we actually have to use that Q value to bootstrap, we look up the Q value of the winning action using the frozen target weights. So an important question then is, why do we do it in this order and not the other way around? So if the idea behind double Q-learning is the weights should be different, why don't I swap WT and W minus? They'll still be different. What do you guys think? I heard some mumbling. Yeah? Yeah, so we will still have achieved double Q-learning because the weights will be different, but we won't be bootstrapping off of the weights in the target network. So we would lose that ability to stabilize function approximation. So here we're both stabilizing a function approximation using a target network and reducing the overestimation by this double Q-learning trick. Okay, so that was the first one. The second one is called prioritized replay, and we need a little bit of history here too. So again, everything about experience replay is a bit off topic here because this is really fundamentally about model-based reinforcement learning, which we haven't talked about and probably won't get to. But as I said before, the idea behind model-based reinforcement learning is just take your data, use it to build a model of the world, and then plan using the model instead of using the data to directly estimate the value function or the policy. So suppose you're doing that. Suppose you have a model-based algorithm, the data goes into the model, and then you plan on the model. What you would like to do is reduce the computational expense of the planning step. So in this sort of archetypal model-based reinforcement learning setup, every time you get a new data point, you update your model, and when you update the model, you have to replan. But planning is expensive, computationally expensive. So you'd like to reduce that cost. So the idea behind prioritized sweeping, which Moore and Atkinson proposed in '93, was that we can make this planning process more efficient by focusing our planning updates, so like, our value iteration updates, we can focus them on the parts of the model that changed as a result of the new data point that came in. So you have some model, right? Then you go out in the world and act, so you get a new data point about some state action pair. You update your model, but only that one cell in your model has changed. So rather than replanning everything, you can just do some planning updates that start from that part of the model that changed and emanate outwards. So the idea was that they maintain a priority queue of the parts of basically the state action pairs that are the highest priority to update. And the first state action pair that goes into that queue is the state action pair that you just experienced out in the world and that caused you to update the model. Then once you've updated that, you look at all the predecessors of that state action pair, that is, all the state action pairs from which you can reach the state action pair you just updated, and you look at all of them and you say, if I were to perform an update based on this state action pair, what would the temporal difference error be? That temporal difference error is your priority. You put it into the priority queue ranked by that priority, and the updates you perform are always sampling the highest priority, taking the highest priority sample from this priority queue. So this was an algorithm which greatly speeds up the planning step in a model-based reinforcement learning setting. So prioritized replay was kind of stealing this idea and applying it to experience replay in a deep reinforcement learning setting. So the motivation was, DQN used experience replay because learning a true model was too hard. So you want to learn a transition model that is useful for planning in Atari, good luck. Like many people have tried and failed. So DQN succeeded because it didn't rely on building an accurate model. Instead, it just did experience replay. So given that we have this sort of poor man's model, how can we get the advantage of prioritized sweeping in this kind of semi-model? So the idea in prioritized replay is all the data goes into your replay buffer, but instead of sampling mini batches from this buffer uniformly, we sample them with a probability that's based on their TD error. So basically, we compute a priority for each sample in the replay buffer, which is based on the TD error. There's a kind of fudge hyperparameter here that determines how we weight the TD error. And then we sample from this buffer according to that probability. So this, again, means that we can reduce we can learn more quickly because for a given size mini batch, we can make more learning progress because that batch is more likely to contain samples that are actually useful for improving our function approximation because we will have samples of higher priority. Okay, that was the second idea. The third one is called dueling networks. So dueling networks are based on the idea of what's called an advantage function. We'll see that a lot more about advantage functions tomorrow, or maybe today at the rate we're going, because they're used throughout policy gradient methods. But the idea behind an advantage function is just, the advantage function is just the difference between the Q function and the value function. All right, so it's for some given action, how much better is this action than the expected action where the expectation is with respect to the current policy or the optimal policy, right? So this value function, right, the value of being in this state, computing this value involves taking an expectation across the actions according to the probability distribution over actions specified by your policy. So here we compare, if I were to take this action, how would that differ than what I would do in expectation? So now the idea behind dueling networks is that this Q function that we're trying to estimate using DQN, we can decompose this as a sum of two parts. We can say the Q function is just the sum of the value function and the advantage function. So that's what's shown in this figure here. So this is like a network architecture. You've got some convolutional layers and then some fully connected layers. But you have, in the fully connected part, you split into two different parts. So this here thing, this part of the network has only one output. This is just V of S. And this part of the network, it has many outputs. This is Q of SA for all A. Oh, sorry. This is A. This is the advantage function. This is A of SA for all A. And if I sum those two together, then I get my Q estimates, which I update using exactly the same loss function I would use in DQN. And it turns out this is a much better architecture. So separating the Q function into this V and the advantage function makes it much easier to learn the value function. However, we have a kind of identifiability problem, which you can think of as saying, like, if I told you Q, and you had to guess V and A from it, you might not be able to do it. So Q does not uniquely identify V and A. So I could think of many V's and A's that would result in the same Q. So in order to address this identifiability problem in the dueling network problem, this advantage estimate that's represented by this part of the network, it doesn't actually represent the advantage function. It represents the advantage function plus some offset. And that offset is the value of the best action. So here we take a maximization. So what we're doing here is basically encoding in the network architecture the prior knowledge that for the best action, the advantage should be 0. Right? So if I'm learning the value of the optimal behavior, then for the best action, the advantage should be 0, and everywhere else it should be negative. So this thing together, these two terms then together become the advantage. And then here's where the hacky part comes in. This maximization is kind of unstable, right? So this is, as I change my value function, as I change my advantage estimate, this max can change discontinuously. So that can cause stability problems in learning. So it turns out to be better to do the learning using an average instead of a max. And then the intuition for this term becomes a bit more opaque, but the learning is stabilized. The average changes gradually, whereas the max can change suddenly. Okay. So the next trick is multi-step targets. This is a concept I did mention already. So, we talked about this middle ground between Monte Carlo methods and temporal difference methods. So temporal difference methods do one-step updates. You get one sample return, and then you immediately bootstrap off the next state. But I can also do n-step updates, where I accumulate n rewards, and then bootstrap off of the value n states later. And we can mix those however we want using eligibility traces with this lambda parameter. Now, typically, eligibility traces are used with on-policy methods. So you have TD lambda, you have sarsa lambda, you have on-policy methods that use eligibility traces to mix these different n-step returns. A lot of people have tried very hard to make Q-learning methods that use eligibility traces, and there are a number of different approaches for doing that. Like several different Q lambdas have been proposed. The difficulty there is that because Q-learning is off-policy, once you start learning from an n-step return where n is greater than 1, the portion before the bootstrapping may not be consistent with the policy that you're learning, right? So if you're learning off policy, you're trying to learn about some policy pi, but the data was gathered with pi prime. So if n is greater than 1, then that target will include a partial return. And that partial return will be gathered according to probabilities determined by pi prime, not pi. So that raises an issue in doing eligibility traces off policy that you don't have on policy. So all the different Q lambda variants deal with this in a different way. You can do importance sampling, or you can say, I'll just ignore any trajectories in which an exploratory step was taken that would cause it to be off policy, but none of them work very well. Once deep reinforcement learning became popular and all the sort of, shall I say, heuristic mindset of deep learning engineers started to dominate, people said, oh, who cares about any of that? Let's just build this multi-step DQN target. So they said, okay, we know the one-step target in DQN probably is not the sweet spot of the bias variance trade-off. We're bootstrapping off of after one time step, so we have a lot of bias because we're leaning heavily on this Q function. We probably do better by giving away some of that bias in exchange for some variance by having bootstrapping later and including more sample returns. So that's exactly what they did. They just said, okay, we'll just sum up some sample rewards. This is like a partial return that sums up some rewards for the first n steps, and then we bootstrap after n steps. And what is this update? What is this update target? Is it on policy? Is it off policy? Nobody really knows. This part is on policy. This part is off policy. Theoretically, it's baffling, but it works pretty well. So the conceptual difficulties of off policy are just swept under the rug, and the bias variance trade-off is optimized to improve performance. Okay, the next idea is arguably even more counterintuitive. So this is called distributional reinforcement learning. So the idea behind distributional reinforcement learning is that when rather than just trying to learn the expected value of the return, we're going to try to model the whole distribution of the return. So given a stochastic policy and a stochastic MDP, if I'm in some state and I follow this policy in the future, there exists some distribution over the returns that I will accrue. So maybe sometimes following this policy I'll get a high return, sometimes I'll get a low return, maybe it's Gaussian, maybe it's multimodal, who knows. But that distribution exists. Canonical reinforcement learning is all focused on just estimating the mean of that distribution. And the idea behind distributional RL is let's estimate the whole distribution. Distributional RL and distributional methods for decision theoretic planning are old. They go back many decades, but they have until recently been used only in risk-sensitive settings. So let's suppose you have an application where you actually don't care about the expected value. You care about some other objective that depends on the variance. So, for example, you have a risk-averse objective. Suppose you're trying to use reinforcement learning to decide how to invest in the stock market. Well, it's very common for investors to take a risk-averse approach where you say, okay, I'm willing to accept a lower expected return on my investments if I can reduce the probability of like losing everything in a crash. So that means, you know, you want to maximize an objective that depends not just on the expected value, but on the variance. So you might, for example, be penalized for having too much variance because you're trying to be risk averse. Or there can even be settings where you're risk seeking, where you would reward variance. So I think a good example of this is like, you know, it's the final of the World Cup and there's 3 minutes left on the clock and you're down by 1 goal. What do? You start doing crazy stuff like you pull out the goalie. You start doing strategies which in expectation you think will lose, but which there's some probability, there's some tail events, you know, that this crazy strategy could generate in which you might win. So even though in expectation you'll lose, you have sort of like a one shot, maybe things will play out your way and you'll have a chance to score a goal, and that's all that matters. So sometimes you would even want to be risk-seeking. But the point is, risk-sensitive, risk-averse, risk-seeking or risk-averse, sometimes you want to be risk-sensitive. If you want to be risk-sensitive, you need to reason about this whole distribution, not just estimate the expected values. That was the original motivation for distributional RL. But recently, people started saying maybe distributional RL is useful even in settings where all we care about is expected value. I'm sure you're going to ask me why. And the answer is not entirely clear. There are some hypotheses about this. So one hypothesis is that it's related to this notion of auxiliary tasks. So I mentioned earlier, you know, you may have a setting where the reward is sparse, so you're not getting enough feedback from your reward function, but there are a lot of related tasks you could solve, like predicting things about the world or maximizing some other things that are related to your reward function that might not directly solve the task, but that might, for example, help you train the early layers of your deep neural network so that you have some useful features that later when the reward comes in, you can learn more quickly. So one hypothesis is that when you do distributional RL, you're basically introducing a bunch of useful auxiliary tasks because you have to basically fit this whole distribution instead of just approximating the expected value. So you know, instead of having TD error, you have a KL divergence. So you have this whole distribution to try to match up. It's a richer source of feedback. So there was a recent paper by Imani and White where they tried to do, in a supervised learning setting, they tried to do some controlled experiments to try to figure out under what situations does this distributional approach improve performance and why. And that paper, at least in the particular experimental setting that they looked at, that paper seemed to rule out this hypothesis about auxiliary tasks. So they did experiments where the distribution that you're learning has only one parameter. So there's still only one target to fit. So there are no auxiliary tasks, and it still helps. So it seems like it might have something to do with smoothing the loss function. Nobody really knows. The most important thing to understand about distributional reinforcement learning is that this distribution that you're learning, it models aleatoric uncertainty, not epistemic uncertainty. So what is the difference between aleatoric and epistemic uncertainty? Epistemic uncertainty is like Bayesian uncertainty. Epistemic uncertainty is the uncertainty represented by your prior. So if your prior has not concentrated around a single state, then you have epistemic uncertainty about the state. So it refers to, it's uncertainty that arises from your lack of knowledge about the world. So in the limit of infinite data, epistemic uncertainty goes away. Aleatoric uncertainty is uncertainty that is a consequence of the stochastic nature of the world. So, like if I have a stochastic MDP, then the transitions from one state to a next are modeled in an inherently stochastic way. So it doesn't matter how much data I get from that MDP. I could have a billion, a trillion, a zillion data points from that MDP. I will still have aleatoric uncertainty in the sense that when I take an action in a state, I don't know what the outcome is going to be until it happens. So, like if you have a fair coin, no matter how many times, so if you have a fair coin and you flip it a billion times, your epistemic uncertainty about whether that coin is fair will go away. But your aleatoric uncertainty about if I flip this coin, will it land heads or tails, that remains. So what is distributional RL modeling? It's modeling the aleatoric uncertainty in the return that arises as a consequence of the inherent stochasticity in your policy and the Markov decision process. There's nothing Bayesian about it. There's no epistemic uncertainty. There's no notion of anything that concentrates in the limit of infinite data. Okay, this is the last trick, and this trick is called noisy nets. So noisy nets is kind of a way to improve the exploration in DQN. So DQN used epsilon greedy, the simplest form of exploration. And there's been a lot of research since then about smart exploration and deep learning, a lot of interesting developments. In Rainbow, they used one of the simplest methods, which is called noisy nets. And the idea is just we take a linear layer in our network, and we replace it with this layer that also has these noisy components. So we have some extra parameters here, and these parameters are then element-wise multiplied by some source of noise, like some Gaussian noise that's just injected into the network. Again, this is a case of it not being totally obvious why it works. So one sort of story about why it works is that over time, the network can learn to ignore the noisy stream. So these parameters can just learn to sort of set them to 0, and over time it will ignore the noise, and it will perform better once it figures out how to learn the noise. But learning to ignore the noise takes time, and until it's had a chance to ignore the noise, it will then continue to explore those states. So we can think of noisy nets as like an automatic way of having a state conditional annealing of the exploration. So the noise introduces some exploration, and as you learn to ignore the noise, your exploration goes down. So, in general, you want to explore less over time because your uncertainty is decreasing, but you're not really sure how to set that schedule. This is an automatic way to set that schedule in a different way for each state. Whether it's a good way to set that schedule is another question, but there's some evidence for its empirical success. Okay, so those are the different tricks in Rainbow, and a sort of limited window into some of the algorithmic developments that have come just for DQN since the original release of DQN. That concludes this set of slides. Let me see if you guys have any questions, and then we still have about 20 minutes, so I would propose we go ahead and make a start on the policy gradient slides that were designed for tomorrow, which means if we keep up this pace, who knows, maybe we can even talk about model-based RL before we run out of time tomorrow. But this would be a great time to ask any questions about anything we've discussed today. Yeah. It like replaces epsilon greedy. So I'm not sure if I heard your question. Instead of epsilon greedy, yeah. I mean, of course you can put the two together, but and who knows, that might be better, but that's not the idea. Other questions? Yeah. So possibly my terminology is confusing here. So this thing here is not a total return. It's just it's a partial return that sums up the rewards only in the first n steps. Does that answer your question? So it's not double counting because the first term represents the rewards in the beginning, and the second term represents the rewards after bootstrapping. If n equals 1, then that first term is just the immediate reward. Yeah, so, actually my notation looks okay because I've defined that. Yeah, so this, if n equals 1, then this summation will have only one summand, and it will just consist of an immediate reward. So we're reduced to the Q-learning update. Do I have an off by 1 error or something? Ah, I see. Yeah, you're right. There's an error in the slides. You're right. Yeah, that should be st plus n. Yes, that should be st plus n. Thank you. Very, very good observation. Other questions? Yeah. Yeah, so I recently saw a talk actually which described noisy nets as a variational approach where one of the terms in the variational loss has been dropped. So there's another paper called VINE, which is like variational inference for something exploration, which does exactly what you described. So you have a Bayesian neural network where you have like a Gaussian posterior over each of the weights in the network. And then you do variational inference to try to maintain that posterior. And then your exploration is guided by that posterior. So basically, you give some optimism bonus, you give some reward bonus for visiting states where that posterior is not concentrated, where it's broad. And noisy nets is like the same thing, but where one of the terms that would actually make it a variational loss has just been dropped. Yeah. Yeah. Sure. Right. Okay, so this DQN update rule, it looks exactly like the Q-learning update rule for function approximation, except for the fact that the target here is constructed using Q estimates that are based on a different set of weights than the set of weights that are being updated by this rule. And those set of weights come from what's called the target network, and the target network are just the old weights that were frozen at some previous moment in time. So we freeze those weights, we do a bunch of updates using those fixed weights, and then periodically we update the target network. So that's one difference, and then the other difference is that this update is not just performed on a raw stream of data coming in from the world. The data is put into a replay buffer. We randomly sample mini batches from that buffer, and then perform this update rule on those mini batches. I don't have the equations memorized, so I can only give the intuition here, which is, so the TD error is comparing your current estimate of the value function to an estimate of the value function constructed using bootstrapping, using a sample reward and bootstrapping. So these are like comparing two different estimates of the expected value. In distributional RL, you're not trying to learn the expected value, you're trying to estimate the distribution. So analogously, you have your current distribution, your current estimate of the distribution over those returns, and then another estimate of that you can construct by looking at sample returns and then bootstrapping off of the result. So you say, I have a sample reward and a sample next state, and I can use that to construct another distribution. Then what does my error look like? My error is based on the distribution, the difference between those two distributions. And the KL divergence is one way of measuring that difference. Yeah? You mean the stochasticity in the policy? But that's part of the aleatoric uncertainty. So whether you're the one introducing the noise into the world or whether it's part of the physics of the world, it's still aleatoric. I mean, if I'm going to act based on a coin flip, I still don't know how that coin flip is going to turn out until I do it. So I mean, it couldn't possibly be epistemic uncertainty because there's no Bayes rule in this algorithm. There's no prior, there's no likelihood, there's no Bayesian update. There's no algorithmic mechanism to reason about epistemic uncertainty. You know, just like all the methods we've talked about so far, it's a frequentist method. You know, you're estimating quantities. You're constructing estimators for quantities, for unknown quantities, and then computing those estimators based on data that you collect. So it's like fundamentally frequentist model of aleatoric uncertainty. Bayesian reinforcement learning is a very interesting topic, but it's well beyond the scope of this course. Other questions? Okay, how are we doing? Let's make a start on policy gradients, and then I will let you guys go home or move on to your next lecture. Okay. So we'll just do a few slides because we don't have much time, and we'll pick this up tomorrow. Okay, so I mentioned, I guess earlier today, all this function approximation, it enables us to deal nicely with continuous state spaces. It doesn't yet let us deal with continuous actions, because even if we can represent the value function for continuous states and actions, we don't know how to perform the maximization. Either the maximization we need to perform to do an update, like if we're doing Q-learning, or the maximization that we need to perform to act in the world based on the learned value function. So with continuous actions, that maximization is itself a hard optimization problem. So in that kind of setting, we can instead turn to a different family of reinforcement learning approaches called policy gradient methods. And the idea behind policy gradient methods is extremely simple. We just say, look, we have some parameters pi that parameterize our policy, and we're going to directly optimize the policy by performing gradient ascent on the expected return. So what we want to do is find the set of parameters theta such that this quantity j of theta is maximized. And what is j of theta? It's the expected value, it's the expected return, but this expectation is now taken with respect to the states and actions, the states that would be visited by our policy and the actions that policy will select. So, you know, the value functions we've seen already, v and q, these are already expected returns, right? And these expectations are taken across future stochastic events. But those value functions condition on the current state or state action pair. So here, what we have here is like a value function that doesn't condition on anything. So it's just in an arbitrary episode, the expected return of my policy. That's what I want to maximize. So this direct approach, directly optimize the policy, as I already hinted at, it's useful really anytime when this greedification step is hard. Anytime we need to perform this maximization to do an update or to select actions, If that problem is hard, if that doesn't just mean trivially iterating over a small action space, then policy gradient methods are an appealing alternative. And continuous actions are the most commonly occurring example of that case when greedification is hard, although there are other cases. So policy gradient methods can also be used in some other settings when, for example, stochastic policies are preferred. So, with the like Q-learning, you will typically learn a deterministic policy. If you have stochasticity, it's just for the sake of exploration, but you're going to learn a deterministic policy because you're going to take a hard max with respect to the learned Q values. But in some cases, you actually want, at the end of the day, to have a stochastic policy. So, for example, partial observability, another fascinating topic we won't have time to talk about. Under certain restrictions, you can show that for a limited class of policies, the optimal way to behave in a partially observable environment is using a stochastic policy. Similarly, in multi-agent problems, you may need to behave stochastically in order to maintain an element of surprise. Like if you play rock, paper, scissors, you don't want to use a deterministic policy. So in cases like that, policy gradient methods can help you learn these stochastic policies. So more generally, if you have any setting in which the optimal policy is simpler to represent and learn than the optimal value function, then policy gradient methods might be useful because we directly learn the policy. We don't learn a value function and then extract a policy from it. We directly learn the policy. In some cases, that may be easier. Or, again, if we have prior knowledge about how to solve the task, and that prior knowledge is in the form of the policy but not the value function, then we may prefer to use policy gradient methods because they rely on an explicit parameterization of our policy. This actually happens a lot because, you may have prior knowledge that says, this task, the policy will have the following hierarchical structure, or the policy should always do this, and I just don't know, the magnitude of the action it should take or something. You have prior knowledge about the policy, but there's still something left to learn. Whereas value functions, they tend to be something that humans do not have a lot of intuition about. So prior knowledge that would help you parameterize your value function is much harder to come by. So we're going to do gradient ascent on the expected return, which means we're going to be converging to a local optimum. So that's a limitation we have to swallow. And sort of the main challenge in policy gradient estimates is, in policy gradient methods, is tackling variance. So we won't know the true gradient to follow, so we're going to have to estimate it from our interaction with the world. That estimate is going to have high variance, and making policy gradient methods effective often comes down to finding clever ways to control the variance. Okay, so let's take a simple case first to derive a policy gradient that we can actually follow to improve a policy. So in this simple case, we have an MDP that lasts only one step. So there are many possible states in this MDP, but when the episode starts, one of those states is sampled from this distribution row, and then we can take an action, and once we take an action, the game ends. So there's no sequential decision making. But we want to find a policy which is good in expectation across these states, and we're going to do that using policy gradient methods. So we want the theta that maximizes J of theta, which is an expectation across the states and the stochastic actions of our policies of, basically our reward function, the immediate reward that we'll receive in this one-step MDP. So this expectation is just a sum over the states and actions of the rewards. And okay, we want to maximize this, so let's take the gradient so we can perform gradient ascent. The gradient looks as follows. We can move the gradient inside these summations. Now we have the gradient of the policy with respect to theta times the reward. So you might think, okay, great, we're done. That was a little bit of very simple calculus. Now we have our gradient, we can just follow it. But the problem is, of course, we aren't able to actually compute this gradient. So what we're going to need to do is estimate it from data. And this gradient is not written in the form of an expectation. So there's no obvious way to convert it into something that we can estimate from samples. So this is where a crucial trick comes in called the likelihood ratio or score function trick, which just converts this gradient into something that looks like an expectation so that we can estimate it from samples. So here's the idea. I just take this gradient that I already derived, and inside the inner summation, I both multiply and divide by the policy probabilities. Okay, so I haven't changed anything because I multiplied and divided. Now I take this term here, and I note that this is the result of taking the gradient of the log policy probabilities. All right, so this is just the definition of the derivative of the log plus an application of the chain rule. All right, so the derivative of the log will give me 1 over pi, and then I'll have to use the chain rule, so I'll have to take the derivative of the thing inside the log. That will yield the numerator. Okay? So that yields this line here. Now, because of this probability here, I can reinterpret this thing as if it was an expectation. So this is now my probability, so this thing again becomes an expectation. So this quantity now I can estimate using a simple Monte Carlo approach. I can interact with the world, get a sample return, use it to compute this sum end and the expectation, and then that's a noisy estimate of the gradient that I can follow. So this is the likelihood ratio or score function estimator, classic trick for estimating gradients, which is used throughout policy gradient methods. If you're familiar with the reparameterization trick, that's kind of the other sort of main gradient estimation trick that's used in machine learning. Okay, so the sort of fundamental result of the of policy gradient methods is the policy gradient theorem, thanks of course to Sutton. So Sutton actually initially was very against policy gradient methods because he thought everything should be based on value functions. But then he sort of there was a long period in which Sutton was not active, doing active research. He was actually quite ill. He made a recovery, and when he came back, he sort of had a change of heart, and he looked at these policy gradient methods that were developed, and he sort of got on board and unified everything together in the policy gradient theorem, which is kind of the foundation of modern policy gradient methods. So the policy gradient theorem uses an unrolling argument to basically extend this idea that we just saw to a general MDP. So everything we just derived was for this one-step MDP. The same principle applies for an arbitrary MDP. The only thing is that now this expectation is with respect to this funny distribution, rho pi, which is called the discounted ergodic occupancy measure. So we can think of it as if we ignore the gamma term for a moment, we can think of this as just like the on-policy distribution, which we already saw in function approximation for doing, for weighting the mean squared error. So given that I'm using this policy, and if I don't know anything else about, how long I've been in the episode, what's the probability of being in a certain state? Okay? So it's so that's the ergodic occupancy measure. So it's the probability of a state of an agent occupying a certain state under the ergodic distribution induced by its policy, but now discounted, now weighted by this discount factor. So it's actually not a proper probability distribution, and things don't sum to 1 because of this discounting. But it allows us to write this expectation of the quantity that we want to maximize in this general MDP. Okay, now this expectation can be estimated using sample returns, yielding an algorithm called reinforce. So instead of this expectation, which of course I'm not able to compute, I just say, let me just take my policy, interact with the world for one episode, and then let me take each sample from each time step in that episode and treat it as if it was a sample from this discounted ergodic occupancy measure. Okay, so this yields then an estimate of my gradient. And so this is just a summation across all of the samples that make up the episode in which I gathered the data, and the rest is just what we saw before. So this is the definition of the gradient that resulted from the application of this score function trick. Now here, what is this thing? This is the sample return. So at the end of the episode, I accumulated some total reward. That's what I'm going to stick in. So here in my policy gradient theorem, I was told I needed to multiply the gradient of the log policy probabilities by the true Q value. Of course, I don't know the true Q value, so instead I just stick in this sample return. So this part at least is unbiased. but will have a lot of variance. So this is an algorithm that Williams proposed and we just called reinforce. So I think maybe this is a good moment to stop. Tomorrow we'll pick up again with policy gradings. We'll talk about actor-critic methods, where we're going to have replaced this target with something, with a value function that we learn, and which will have lower variance. So I will see you guys tomorrow for the conclusion of this tutorial series, and we'll finish policy gradient methods and see if we can also maybe say a few words about model-based methods. Okay, I will see you guys tomorrow.